Reality feels solid, right? Objects move in straight lines, cause follows effect. It's all predictable, but that's just the illusion. Because when you dig into quantum physics, something bizarre starts happening. Particles stop behaving like they should. They don't follow one path, they follow every possible path. All at once. Light, electrons, even you. The deeper you go, the more it starts to look like reality is glitching. And today, we're showing you the proof. Let's start with a simple question. How does light know where to go? Imagine you're on a beach. Your friend is out in the water struggling. You need to get to them fast. So how do you do it? You could run straight at them, right into the waves, shortest distance. But you run faster than you swim. So maybe you run further down the beach first, then cut in. Now you're traveling farther, but swimming less. Turns out, there's a sweet spot between those two paths. A fastest path, not a straight line. And here's the twist. That's exactly what light does. When light moves from one medium to another, like air to water, it bends. But it doesn't just bend randomly. It chooses the fastest possible route. That's a real physics principle. Light finds the path of least time. The weird part? Light doesn't know where it's going. It doesn't plan ahead. And yet, somehow, it always picks the best route. At first, that seems easy to explain. Local interaction, right? Light hits the boundary, then bends. End of story. But no, that's where the illusion begins. Because quantum physics shows that light doesn't just pick one path. It tries all of them. This glitch in how light moves comes down to something called action. Back in the 1700s, a scientist named Maupertuis proposed that objects always take the path that minimizes action, which he defined as mass x velocity x distance. Later, Hamilton refined this. Action became the integral over time of kinetic energy minus potential energy. Sounds dry, but stay with it. This is where everything changes. At first, action was just a tool. It helped solve tough physics problems when Newton's laws got messy, but then quantum mechanics showed up, and action went from a useful shortcut to the foundation of reality. Picture Germany in the 1890s. Electric lights are the hot new thing, literally. Scientists are racing to figure out how to make bulbs more efficient. That means understanding how materials glow when heated. They study a perfect black body, a metal cube with a hole that absorbs and emits radiation flawlessly. Inside, waves bounce around. Theorists expect that shorter wavelengths, higher frequencies, mean more energy. But the math says there should be infinite energy at short wavelengths. Well, that's clearly wrong. They called it the ultraviolet catastrophe. Enter Max Planck. Desperate, he breaks the rules. What if energy only comes in chunks? He proposes energy is quantized, restricted to little pieces, each one based on frequency, E equals hf. This one equation fixes the catastrophe. It matches the data. But Planck doesn't understand why it works. He calls it a trick, a band-aid. But that trick launches quantum mechanics, and h, Planck's constant, becomes the quantum of action. Every process in nature, Planck proposes, happens in whole multiples of this tiny number. Action, not energy or force, is what matters. Planck's idea spreads. Einstein picks it up and runs with it. He says light comes in packets, photons, and explains the photoelectric effect. Niels Bohr uses the same logic to solve another mystery, how atoms don't collapse in on themselves. Nominal distances as well as the electrons can only orbit at certain distances. Those that give them angular momentum equal to whole multiples of h bar, Planck's constant, divided by 2p. Why? No solid reason, just a guess. But it works. Then Louis de Broglie comes in with a wild idea. If light can act like a particle, maybe particles act like waves. He gives everything electrons, basketballs, a wavelength. And that wave can only fit around an atom if it forms a standing wave. That's why only certain orbits are allowed. That's why action is quantized. Now, it's not just a math trick. There's a reason particles take certain paths. They're waves. And waves do weird things. You've probably heard of the double slit experiment. Shoot electrons through two slits. You get an interference pattern, like waves. Even if you shoot them one at a time, they still interfere with themselves. That means each particle goes through both slits at once. Not one, not the other, both. Now here's where things get nuts. A student once asked, what if you had a third slit, a fourth, a fifth? What if you had infinite slits and just got rid of the screen entirely? The logic doesn't stop. If a particle can go through two slits at once, then it must go through every possible path in space. That includes paths that loop, curve, bounce off the moon, or go back in time. It sounds insane, but mathematically, it has to be true. Physicist Richard Feynman took this idea and turned it into a complete theory. He said, to figure out how a particle gets from point A to point B, you have to consider every possible path. Not just the straight line, all of them. Each one contributes a little complex number, an arrow, that spins as the particle travels. The angle of that arrow depends on the action of the path. Add up all the arrows, square the result. That gives you the probability the particle shows up at point B. But here's the catch. Most of those arrows cancel out. The only ones that add up neatly, the ones where the action changes the least. Those arrows all point roughly the same way. They interfere constructively. That's what we see. Okay, so this all sounds like deep theory, but can we actually see it? Yes. Casper built a demo using a light, a mirror, and foil, with thousands of tiny lines per millimeter. Normally, light reflects in a single direction, but with this foil, basically a diffraction grating, something weird happens. Light appears in places it shouldn't. Reflections show up at angles where the mirror alone can't explain them. Why? Because the foil blocks out paths that cancel each other out. What's left is a path that shouldn't be there, but now is, because the destructive interference is gone. It's not a trick, it's quantum physics, live on camera. Even with a laser, you can see the light jump to a new location when the foil is added. Take it away and the reflection disappears. Put it back and it comes right back. It's visual proof that light really does explore every possible path. We just usually don't see them because they cancel out. So why does the world feel so normal? Why don't we see particles flying in loops or bouncing off invisible walls? Because of scale. Planck's constant is tiny, like, really tiny, 10 to the minus 34. For big, everyday stuff, any change in action causes so many spins of those little quantum arrows that they end up pointing in random directions. They cancel each other out. Only the path with the least action survives. That's the one that feels normal. But for tiny particles, electrons, photons, the action is small enough that more paths survive. That's why quantum effects show up at small scales, and why the macroscopic world feels solid, but underneath, it's chaos. Order only emerges because of interference. So yeah, reality is glitching. Light doesn't travel in a line. Electrons don't follow one path. They try every path, and the universe picks the one that makes the math line up. And if that's not weird enough, this principle least action might be the real core of physics. Not force, not energy, action. That's what theoretical physicists chase, the perfect Lagrangian, one equation that spits out all the laws of nature. We haven't found it yet, but when we do, it'll be the key to unlocking everything. Because when you trust quantum physics, the glitches start to make sense, and suddenly, reality doesn't seem so real anymore. If this cracked open your view of reality, there's way more where that came from. Hit subscribe, tap like, and let's keep pulling at the threads of the universe together. Thanks for watching.